In this video, I'm going to talk about the classical harmonic oscillator and some of the things that actually apply to the quantum harmonic oscillator. So Hooke's law says if you have a spring at rest and you pull on the spring, there's a restoring force that wants to pull it back. Or if you compress a spring, there's a force that wants to push it back out. Okay, so the force you have to apply is a linear function of the displacement. So x is not the position, it's the how far away from the equilibrium that spring distance is. And if you say F equals ma, solve Newton's law where mass times the second derivative of position, solve for that, well, again, you have second derivatives equal to themselves, and so you have functions like sines and cosines. The important thing to recognize is that the potential function here is a parabola. All right. So if the force is minus the derivative of the potential, then the potential function is going to be 1/2 kx squared. And so it's a parabola, and k is the curvature or the second derivative, and that's a constant for a parabola. Okay, and so when you take the second derivative, you get k. So the harmonic oscillator in principle can be displaced to plus and minus infinity. However, real bonds, which is what going to be our model for a spring, is not going to be able to be stretched to infinity. So at some point this model breaks down. However, if the bond does not vibrate very much, it turns out it's like being in the bottom one of these, and so it doesn't really affect the result that, you know, when you stretch it a long way, it's no longer harmonic. So we're going to do diatomic molecules again as our main example. So it'll have mass 1 times mass 2. Now the distance r is going to be the equilibrium distance because it's going to be changing during the vibration. So we'll call it Re. E stands for equilibrium. And it turns out the vibrational frequency in radians per second, omega, is just the square root of the force constant divided by the reduced mass for a diatomic vibrator. Okay, so what happens in quantum mechanics? Well, in quantum mechanics, the energy is quantized, okay? And it's going to be multiples of h bar times omega. It's not quite an integer multiple. It's actually an integer plus 1/2 multiple of h bar omega. So the energies are going to be 1/2 h bar omega because the lowest V quantum number is 0. Then the next energy that you can have for the harmonic oscillator, that corresponds to something with a certain force constant and reduced mass that gives the frequency omega. H bar omega times 1 plus 1/2 is 3/2, and so the lowest one is 1/2 h bar omega, then 3/2, then 5/2, 7/2, and so on. And so it's actually quite common if you run a Spartan calculation, for example, for any quantum mechanical or even mechanical method, the vibration frequencies that you get are calculated with classical mechanics, some sort of parabolic function. You impose more or less the condition for the quantized energy on top of that. Since if omega is correct, well, there's no need to use a quantum mechanical model to calculate the energy levels. All you do is you just say, okay, I know the lowest one's V equals 0, and so it's 1/2 h bar omega and so on. So what you might see plotted on top of the parabolic curve is the energy at which V equals 0. So this is h bar, 1/2 h bar omega over the minimum. So this is called 0-point vibration energy. Okay? So when V equals 0, the energy is not 0. All right, and so the next one's going to be 3/2. And the thing about this is that the difference in energy is h bar omega. The next one, V equals 2, that difference is also h bar omega. So what this means is if you have a molecule and you're absorbing light that corresponds to the frequency omega, And then you cannot tell the difference between a molecule going from the 0 to 1 quantum level and the 1 to 2 quantum level. All right. Now, it turns out that at room temperature, if you have an equilibrium, a thermal equilibrium, most of the molecules are in the lowest energy ground state. That's because there's not enough thermal energy to excite to V equals 1 for most of the time. Okay, so that's it for the harmonic oscillator. We'll actually have a video on the quantum oscillator where we take the wave functions and talk about what their functional form is, what they look like, and the phenomenon called tunneling.